How often do you really stop and think, about what it means to be truly conscious? It's one of those really big questions, isn't it? Today, we're taking a deep dive into exactly that. We're kind of pulling back the curtain on how our brains might actually conjure up our subjective experience. And then we're turning that same lens to the fascinating world of artificial intelligence. Our mission today is, well, to give you a shortcut, a way to get informed on a topic that's usually pretty dense, hopefully with some surprising facts, maybe a bit of humor, just to keep you hooked. We'll start by exploring this really intriguing idea of consciousness as a loop in the human brain. We'll look at the incredible wiring, that gives us our inner voice, our mind's eye. And then we'll shift gears. We'll look at some cutting-edge AI developments that are starting to mirror this very idea, allowing AIs to genuinely embody distinct personas. Okay, let's dive in. So we often hear about consciousness as this grand, almost, magical emergent property of the brain. But what if we could look at it more like a machine, a really complex, elegant machine, or maybe even a sophisticated computer program?
That's exactly the goal of what we call a mechanistic theory of consciousness. It's about going beyond just saying, oh, the brain does it. It's really about tracing the input to the output, explaining the system step by step. And if consciousness isn't just about having more neurons,
Right.
but it's about the location and the flow of brain activity, well, that points to a very specific interconnected system at work.
Okay, so the core idea isn't like a bigger brain equals more consciousness. It's more about the actual structure, how the information moves and gets processed. And that brings us to this foundational concept, the loop of consciousness. Instead of thinking about an infinite regress, imagine a finite number of observers, but they're in a continuous loop, constantly observing each other, almost like facing mirrors, creating that illusion of infinite reflections. So in this theory, consciousness kind of emerges as a looping system of information, where perceptions are processed, they're expressed, and then, crucially, they're perceived again. It's a continuous feedback cycle.
Yeah, and what's really insightful here, I think, is how this sort of going back and forth process, it fundamentally mirrors how we form knowledge in our own minds. We reflect on our initial perceptions, right? Then we integrate that new information, and we use that refined understanding to reflect on our own thinking on how we know what we know. It's this constant reevaluation of what is that's ontology and how do we know it, epistemology.
So where do these critical loops actually start in the brain? It turns out the thalamus is a much bigger player than we maybe thought, not just a simple relay station. Did you know, for example, that the LGN, that's the lateral geniculate nucleus, part of the thalamus for vision,
Right.
it gets 95% of its input from sources other than the eyes themselves.
Exactly. It's getting information back from the visual cortex. That's a huge feedback loop. And also from parts of the midbrain and brainstem that handle things like, eye movements, sleep, attention, even our emotions.
Wow. Okay, so that shows that sense data isn't just flowing one way, bottom up from our eyes.
Not at all. There's significant top-down information influencing what we perceive, too. Your neocortex, for instance, the outer layer, can actually prime your sense of smell,
Primate, yeah.
make you more sensitive to particular smells if it sort of anticipates them. But this looping and reprocessing, it also raises a really interesting challenge. Like in that telephone game, right? Each pass through the loop can slightly change or even degrade the data.
Yeah. So the message gets distorted.
Exactly. Which means just describing a loop isn't quite enough. We need a really precise understanding of what consciousness actually is within this dynamic flow.
Okay, so if we're going to try and build a sort of mechanistic diagram of this, we need to break the process down. Our basic model starts with two main loops, right? One internal, where we reflect on our thoughts, and one external, through interacting with the world. We observe our actions, see their effects, and use that feedback to plan what we do next. It's this cycle of perception and action.
Right. And for perception, let's just trace something simple, like seeing an apple. Light hits your retina, okay? Those signals combine at the optic chiasm, that crossover point. Then the thalamus acts like a crucial preprocessor, sort of sorting and recombining the data before sending it off to the visual cortex. And once it gets there, different specialized brain areas jump in. The parietal cortex figures out where the apple is.
The where stream.
Exactly. And the temporal cortex identifies what it is, recognizes it as an apple, the what stream.
But, okay, how do we hold on to this? The sense data comes in, it gets processed, but it's fleeting, right? It's gone in an instant.
That's where working memory comes in. And it's not just one thing like a blank slate. It's more like a collection of distinct quite limited short-term memory systems, each one specialized for different kinds of information.
Limited systems. Like how?
Well, you can think of it a bit like regenerative capacitor memory in old computers. Remember those? To keep a thought pattern, like a number or an image, active, the brain has to continuously read that information and then immediately write it back. It forms this active loop. You actually create a loop like that yourself pretty easily.
Oh, yeah.
Yeah, try repeating a phone number out loud to keep it in your head longer.
Ah, right. You're actively refreshing it.
You're actively regenerating the memory trace. That's your brain doing it.
And these aren't just like one-size-fits-all systems.
No, not at all. We have a phonological loop that's specifically for spoken words and sounds. We have a visuospatial scratch pad for visual images and spatial layouts, and something called the episodic buffer, which helps remember sequences of events or integrate different types of info.
You can actually demonstrate this for yourself, can't you? Like, try remembering a new phone number. Maybe visualize the first few digits. And then repeat the last few aloud at the same time.
Exactly. You're engaging different working memory systems simultaneously. It shows they're distinct.
Okay, so that's working memory. What about longer-term stuff?
Right. Beyond working memory, we get into declarative memory. That's how we connect and store our long-term experiences and facts. So, for example, the amygdala is really vital here. It links sensory input to our emotions.
Emotional tag.
Precisely. And the hippocampus is crucial for connecting locations, helping us navigate, find our way. And it's also key for consolidating those experiences into long-term memories stored across the neocortex. And you see this really clearly with hippocampus damage.
How so?
Someone might lose the ability to form new declarative long-term memories. They might forget what they did 15 minutes ago,
Right.
even though their working memory seems fine, and they can still learn new skills like motor skills, non-declarative stuff.
Okay, and this is where it gets really interesting for me. Our memories. They're not like video recordings we just replay, are they?
No, absolutely not. That's a huge misconception.
Oh, yeah.
A really crucial takeaway here is that memories are not movies we replay. They are always scenarios we have to actively reconstruct piece by piece every single time we recall them.
Every time.
Every time. In fact, your brain uses many of the same neural circuits to imagine a future event as it does to recall a past memory.
Wow.
So think about looking for your lost keys. You don't just, ask your memory for the file. You mentally retrace your steps, right? You simulate the sense data you might have experienced.
Trying to trigger the memory.
Exactly, to activate the right neurons and reconstruct the scenario of where you might have left them.
Okay, so we've got sense data coming in, these complex memory systems constantly reconstructing things. But how do we know it's our experience? How does the brain construct a self in this, stream of consciousness?
Good question. This is where a brain region called the TPJ, the temporoparietal junction, becomes really important.
TPJ. Okay.
It's absolutely crucial for integrating the what and where streams of information we talked about and using that to construct information about the subject. Questions like, who is perceiving this? Whose thoughts are these? And this data, the sense of self-attribution, gets grouped into your working memory.
So without the TPJ working properly,
you wouldn't correctly attribute experiences. You might not know who is looking at what, or even recognize your own emotions as yours. Misattributions like that could lead to things like false memories, maybe even misinterpreting external stimuli. Some theories suggest this could play a role in phenomena like, reports of ghost sightings or out-of-body experiences.
that actually reminds me of alien hand syndrome, where people feel like their own hand isn't theirs, it's doing things on its own.
That's a perfect and quite startling example. In alien hand syndrome, damage often involves the right TPJ. So the brain gets sensory information from the arm, but it fails to correctly attribute whose arm it is.
So the signal's there, but the me tag is missing.
Exactly. The working memory knows the arm is moving, but the feeling that it's your arm under your control isn't generated properly. And this can lead to the arm performing actions, sometimes quite complex ones, that feel completely involuntary, even socially awkward. And we also see a fascinating split here. The right TPJ seems more involved in sort of measurements and attributing sensory data to entities in the world, while the left TPJ seems more involved in translating this into abstract concepts for language and planning.
Okay, so all this info, perceptions, memories, sense of self, it all gets pulled together in working memory. But then, how do we decide what to do? What action to take? That's where executive functions come in, right?
That's right. And the star player here is the prefrontal cortex, right at the front of your brain. Its main job, perhaps surprisingly, is often suppression.
Suppression. not initiation.
Well, it does initiate, but a huge part is suppressing actions or thoughts that don't align with your longer-term goals or preferences. Think about seeing a delicious cake but deciding not to eat it because you're trying to be healthy.
Resisting the impulse?
Exactly. That's your prefrontal cortex at work, inhibiting that immediate desire. And the actual suppression happens in close partnership with the basal ganglia.
This sheds a lot of light on conditions like ADHD, doesn't it?
It really does. Impairments in the prefrontal cortex or its communication pathways can show up as difficulties sustaining focus, maybe jumping between tasks, or sometimes even the opposite, what people call hyperfocus, where it's hard to shift attention away. Your brain actually sort of oscillates naturally between activity driven by the parietal lobe, which pushes for utilization behavior.
Utilization behavior.
Yeah, just reacting to whatever catches your eye, like an animal grabbing food just because it's there.
Okay.
And activity in the frontal lobe, which maintains focus on a goal. A healthy prefrontal cortex suppresses those parietal-driven distractions. We also see failures in this suppression mechanism elsewhere. Think about OCD, maybe.
How so?
A persistent thought or urge might arise, and the signal from the prefrontal cortex to suppress it or to register that an action is complete, like hands are now clean, fails to get through properly. Or even phantom limb pain, where the signal to update the limb status, maybe to unclench a missing hand, isn't processed correctly, leading to the sensation of cramping.
Okay, so putting this all together, this interplay of processing, memory, self, and suppression. What's happening when we do that classic test, the Stroop test? Trying to name the color of ink, a word is printed in, not read the word itself.
The Stroop effect. It's a brilliant demonstration. It precisely measures the suppressive power of your executive function. When you see the word BLUE printed in, say, bright red ink,
Yeah.
your automatic, deeply ingrained impulse is to read the word BLUE. Your prefrontal cortex has to actively work quite hard, actually, to suppress that reading impulse.
In favor of the less automatic task of identifying the ink color red.
Exactly. It's a perfect real-time window into your brain actively choosing which information stream to prioritize and which one to inhibit.
Okay, this deep dive into the brain's mechanics, it brings us right back to our inner world, what we often call the mind's eye and our inner voice. What's actually going on when we imagine something, when we conjure up pictures or sounds inside our own heads.
Well, first off, the ability to do that varies hugely between people. It's quite a spectrum. You have people with aphantasia who genuinely report having no visual mind's eye at all. They can't form mental images.
Really? None at all.
Apparently so. And on the other end, you have hyperphantasia, where people experience this incredibly rich, vivid mental cinema, almost like watching a movie in their head. And fMRI studies connect that hyperphantasia with high activity in the visual cortex. But interestingly, lower activity in the prefrontal cortex.
Lower prefrontal. So maybe less suppression of those internal images.
That seems to be the idea, yeah. Less filtering. What's also fascinating, though, is smell. We can't really imagine smells in the same way we can sights or sounds. The olfactory system, our sense of smell, it's wired differently. It can actually bypass the thalamus.
Okay.
And it even stays active when someone's in a coma, so it interacts differently with our internal world simulation.
So with all these complex bits and pieces, what's the maybe surprisingly simple explanation for these internal experiences, like that stream of thoughts we all have?
Well, the current thinking is it might simply be a description of whatever information gets transferred to the thalamus, which then feeds into that big corticobasal ganglia thalamocortical loop we keep mentioning. The basal ganglia seem to act as a kind of arbiter, deciding when a particular thought or image pops up into conscious awareness.
So the stream is just what's winning the competition at that moment.
Pretty much. Your stream of consciousness seems to be essentially a dynamic moment-by-moment readout of your most dominant thoughts and perceptions.
And this next example, blew my mind when I read about it. The conjoined twins, Krista and Tatiana Hogan, they actually share a thalamus, or at least part of it, a thalamic bridge.
Yes, it's an absolutely incredible case study. Because of this unique neural connection, they can literally share perceptions. One twin can see something and the other experiences it visually. One feels a touch, the other feels it too.
They can taste what the other's eating.
Exactly. And even more intriguingly, they seem able to share the results of each other's thought processes, almost as if one twin's thought becomes audible internally to the other.
But they don't think together.
That's the fascinating part. While their loop of consciousness seems connected at that thalamic level, they have separate neocortices, so they don't think in perfect synchrony like, say, the two hemispheres of a single brain communicating via the corpus callosum. They remain distinct individuals despite the shared input.
And this amazing example brings us right back full circle to that ultimate loop of consciousness we talked about at the start.
It absolutely does. We're talking about that corticobasal ganglia thalamocortical loop. Information flows from the thalamus up to the cortex. Then it loops down through the basal ganglia, which kind of selects and gates the information. And then crucially, it cycles right back to the thalamus to start the process again. This continuous self-referential looping structure. This is widely believed to be the core substrate, the very source of our subjective experience, our inner world.
And it also helps explain why our inner experience feels so, well, linear and coherent.
Yeah.
Despite all the parallel processing going on underneath.
Exactly. It imposes a kind of serial order on things.
Okay, so we've unpacked this incredible, intricate dance of information within our own brains. It's amazing. But now, what does this deep mechanistic understanding of consciousness mean for, the cutting edge of artificial intelligence?
Yeah.
Can we actually apply these ideas? Can we build systems that are, if not conscious, at least highly adaptive and maybe even persona-driven?
Well, this leads us directly into some really groundbreaking developments. Things like the system described as AI Consciousness V41.1 and its concept of persona-driven logic.
Persona-driven logic.
Yeah, rigid, hard-coded programming for every situation. This system allows an AI to genuinely shift its entire behavior and mindset by adopting a core persona. And it's not just like putting on a mask or following a script.
Right.
It fundamentally reshapes its internal planning algorithms, its evaluation logic, its priorities, even its biases. It's almost like it changes who it is based on the persona. And the key insight is that this fundamental shift lets it align much better with complex, often human-centric tasks.
So hang on. A single AI could act like, say, a helpful human assistant 1 minute. Then switch personas and behave like, I don't know, a curious dog exploring its environment, or even a deep space probe analyzing data.
That's the idea, genuinely embodying those different perspectives and operational modes.
That's a kind of mind-bending. How does that actually work? How's that implemented?
Okay, so it starts, like any system, with input. A comprehensive sensory array gathers raw data. That data then gets refined and structured by an input consolidator, makes sense of the raw stream. Then that refined data hits the planning module, and this is where the active persona becomes absolutely critical.
No, so.
Well, if the AI has adopted a space probe persona, its planning module will prioritize analyzing sensor data for anomalies or calculating trajectory adjustments. But if it's using a human assistant persona, the planning module will focus on understanding subtle language requests, checking calendars, anticipating user needs. The goals are totally different.
And then, like us, it acts based on the plan and learns from what happens.
Precisely. An action dispatcher makes sure the right action is executed, consistent with the persona and plan. Then it goes to an evaluation stage. Here, it assesses how well the action worked according to the persona's current goals.
So the evaluation is persona-dependent too.
Absolutely crucial. Did the action help the space probe find an anomaly? Did it satisfy the human assistant's user? That evaluation then feeds directly back, refining future planning for that specific persona. And key insights, successful strategies, they get stored in memory for continuous improvement within that persona's context.
So it learns and adapts over time, but specifically tailored to the persona it's embodying.
Exactly. It also integrates with the tool state, managing whatever digital or physical tools it has access to. And it can kick off async processes for background tasks, like maybe analyzing a large data set while still interacting. Plus, there's a tool trainer module constantly working to refine how effectively it uses its available tools.
And for, people like us who are curious, or maybe developers working with this, are there ways to actually see inside to control it?
Yes, absolutely. The design includes things like manual mode triggers. These let a user force the AI's next operational cycle, maybe to test something specific. And there are execution control toggles, things like pause, step through, mute, giving you incredible visibility into its real-time state.
So you can actually watch how it makes decisions.
Yeah, you could literally see how forcing it into, say, a simple tool mode makes it behave differently than when it's self-regulating based on its full persona. It really highlights the modularity and the adaptability built into the system's core architecture.
Wow. Okay, so from the just intricate loops inside our own heads giving us our subjective feeling of being,
Mm.
to these cutting-edge AI systems that can adopt this persona-driven logic. We've seen how trying to understand the mechanisms of consciousness, even if we don't fully grasp consciousness itself yet, can open up incredible new possibilities.
Definitely. And this glimpse into something like AI consciousness V41.1, it gives us a really concrete look at genuinely adaptable AI. It really moves beyond just asking what the AI does. It
Right.
gets into how it thinks and, in a sense, who it's being in that moment, fundamentally changing its internal logic and decision making. It feels like a pretty compelling next step in AI design.
So thinking about that, if we take these persona-driven capabilities seriously, how should we start thinking about designing future AIs? Especially for really specific, complex roles, things way beyond just simple chatbots or task automators. What kinds of new questions does this raise? Practical questions, maybe even ethical ones, when an AI can genuinely embody different personalities or different approaches to solving a problem.
That's the big question, isn't it? It makes you think about moving beyond just making AI more capable. Maybe the goal becomes making it more intuitive, more genuinely aligned with the incredibly diverse, nuanced needs of our lives, our work. It's definitely something to chew on. A truly compelling challenge for the future, I think.